Consider a reaction A plus B gives rise to products. Okay. Say for this reaction, rate can be given as K into A into B. Okay. The same rate can of course be written as Z into F into P. What is this Z? Z refers to collision frequency. We have actually come across this in gaseous state, which actually gives us the total number of collisions. Total number of collisions taking place in unit time and of course in unit volume. It actually deals with all the collisions. Okay. Now coming to this F. F deals with the fraction of collisions occurring between molecules having energy greater than or equal to threshold energy. Okay. So out of the total number of collisions, only those collisions occurring between molecules having energy greater than or equal to threshold energy is given by this F. And finally, coming to this P. P deals with the collisions occurring between molecules approaching in a proper orientation. So it actually deals with orientation. Okay. Now, say this F can of course be given as e power minus EA by RT. Okay. So this is all about rate. Rate can be given as Z into F into P. Now, when concentration of A as well as that of B is unity, I mean 1m, rate becomes equal to K, considering this expression. Rate becomes equal to K when concentration of A and that of B is 1m. Okay. So now K can be written as equal to Z into F into P, right? Because rate has now become equal to K. Now leaving this aside, I mean this F aside, take these two, Z into F, into consideration. Now that can be given as K is equal to A into F is anyway e power minus EA by RT. Okay. Where this A refers to Arrhenius factor or collision factor or pre-exponential factor. And overall, this is Arrhenius equation. Okay. So the important relations are K is equal to A into e power minus EA by RT and F is equal to e power minus EA by RT. Okay. And now for a reversible reaction, if we apply Arrhenius equation, okay, Kf can be written as AF. F refers to forward. E power minus EA of the forward reaction by RT. Okay. Similarly, KB can be given as AB into e power minus EA backward reaction by RT. Now, we know that Kc or simply K equilibrium, nothing but equilibrium constant is equal to Kf by Kb. So this is nothing but AF by AB into e power minus of EA forward minus EA backward by RT. Straight away, we can write it this way. Now, you know this EA forward minus EA backward is delta H. So we can write it as K equilibrium is equal to AF by AB into e power minus delta H by RT. Okay. Then taking log on both sides. Log K equilibrium is equal to log AF by AB minus delta H by RT. Okay. Now this can be, of course, converted into base 10 logarithm. So this is 2.303 log AF by AB minus delta H by RT. Or from this, we can write the final expression as log K equilibrium is equal to log AF by AB minus delta H by 2.303 RT. Now, from this, we can actually give graphs pertaining to endothermic and exothermic reactions. Okay. Let me again take the equation into consideration. Okay. Now this, okay, let me write it. Delta H by R into 1 by T for convenience. So Y is equal to C plus Mx. Now, see, for an endothermic reaction, if we plot a graph between log K equilibrium and 1 by T, okay, then that would be like this. For this, of course, delta H is positive because it is endothermic. Then as usual, the slope is minus delta H by R. Okay. Next, this is of course for endothermic reaction. Now going for the exothermic reaction, it will be like this. So in this case, it will be this. See, because it is exothermic, delta H is negative. Slope, of course, is the same, minus delta H by R. Okay. Clear from this expression. This is Y. This is X. And this is the slope. And this is, of course, the y-intercept. Okay. Now, okay. Now, suppose at two different temperatures, if we consider two different rate constants, see at a temperature T1, if the rate constant is K1, similarly at a temperature T2, if the rate constant is K2, then taking the basic expression into view, that is K is equal to A into e power minus Ea by RT. ln K can be written as ln A minus Ea by RT. Okay. Now, supposing if ln K1 is considered, then it would be Ea by RT1. Similarly, ln K2, ln A minus Ea by RT2. Now, if suppose This is given as equation 1 and this as equation 2. From one end to, we can write the final expression. Log K2 by K1 is equal to EA by R into 1 by T1 minus 1 by T2, or can also be written as log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T1 T2. Okay, that's it.